Welcome. In this little video, I will discuss the data pertaining to the COVID disease in Switzerland and how the number of recorded cases and the number of recorded deaths developed over time. This plot shows the data that is made available by the Swiss authorities. The horizontal axis shows the time that elapsed since the recording of the first case. This was around the end of February this year. The vertical axis shows four quantities. The first quantity is the total number of recorded cases, shown in dark blue. The second number is the total number of fatalities recorded, shown in dark red. The lighter colors show the additional cases and the additional fatalities per day. This quantity is labeled little dn. The total number of cases and fatalities is labeled capital N. The vertical axis shows all data on a logarithmic scale. The right-hand axis shows the same numbers divided by the total population of Switzerland, thus providing the numbers in per 1,000, that is in per mil. Additionally, on the time axis, a few relevant dates have been marked. One important date is the date at which schools closed in Switzerland, which is the 16th of March. I've also marked the 1st of March and the 1st of April for reference. A remarkable feature of this data set is that the number of recorded cases and the number of recorded fatalities increases very rapidly with time. Over long periods of time, this increase is linear on this logarithmic scale with time. In particular, between the 1st of March and the 21st of March, the data shows an exponential increase that is described very well by a single rate. This single rate is about 0.23. That means that the number of recorded cases and the number of recorded fatalities increases by about 23% every day in that period of time. For creating this next plot, we have analyzed some of the data. As a first step, we have performed an exponential fit to the recorded number of cases in the time frame from 1st of March to 21st of March. That is about 3 weeks. We do observe that the dark black line fits the blue data points very well in this period of time. The exponential increase of the number of cases is characterized by a rate which I have mentioned in the discussion of the last plot already. This exponential rate is about 0.23 in this period of time. The inverse of that rate, multiplied with a natural logarithm of 2, gives you the time over which the number of cases doubles. And in this period of time, the number of cases doubled every 3 days in Switzerland. Dividing the natural logarithm of 10 by this rate gives you the time over which the number of cases that are recorded increases by 1 order of magnitude. This time is about 10 days in this time frame. That means in the period of these 20 days, the number of recorded cases has increased by a factor of 100. If no further action would have been taken at this point in time, it would have been likely that the number of recorded cases would have increased in the same way for the days to come. Fortunately, in Switzerland, at the 16th of March, the schools and the universities were closed. The closure of schools and universities has likely contributed to a slowdown of the increase in the number of recorded cases that was observed starting from the 21st of March. This slowdown in the increase of number of recorded cases can also be observed when we look at the light blue data. In the period between the 1st of March and the 21st of March, the number of recorded cases increased every day by an ever-increasing amount, little dn. Starting from the 21st of March, however, that number dn per day remained constant at a level of about 1,000. Before we analyze the development of these rates further, we will first look at the development of the number of fatalities that were recorded in Switzerland. I have analyzed the data that was available for the number of fatalities in the same period of time since the first recorded death up until the 21st of March this year. Also, this data set is very well described by an exponential increase with a single rate. Again, the inverse of that rate multiplied with a natural logarithm of 2 gives one the doubling time of the number of recorded fatalities. And in that period of time, that doubling time was about 2.5 days, which is very, very fast. At that rate, the number of recorded fatalities increased by a factor of 10 in only a little bit more than 8 days. Fortunately, also the rate of increase of the recorded fatalities reduced starting from the 21st of March by some. We will further analyze the change in these rates for both the recorded cases and the fatalities in the next step. As a next step, instead of fitting large data segments of this data set, I decided to always fit the last 7 days of available data and looked at how the rate or the doubling time evolves over time for this data set. Doing this allows us to cope with the fact that the rate at which the number of recorded cases and the number of fatalities changes also with time, as we're taking measures to counteract the spread of the corona disease. In the following animation, you see a fit over the last 7 days shown as a blue line, which is extrapolated over another 13 days as a red line. Then the starting point of that fit is shifted over the data set until we reach the last week for which data is available. In this way, we can extract how the rate of change changes itself with time throughout the situation. We can do so both for the recorded cases as well as the recorded fatalities. Throughout this animation, you can both follow the rate beta that describes the change per day in recorded cases, the inverse of that rate beta multiplied with the natural logarithm of 2, which describes the doubling time, and the time that it takes to reach 10 times as many cases, which you find by dividing the natural logarithm of 10 by the rate of change beta. And the numbers for both the recorded cases and the recorded fatalities are given and animated at the bottom of this plot. When we analyze the number of reported cases and number of reported fatalities over segments of 7 days duration and extract the rate of change from these analyses, we can then plot both the rate and the doubling time of those two quantities versus time. This is done in the plot which is shown here. So in blue, you see the change of the doubling time of the recorded cases over time periods of 7 days versus the time of the last day that is considered. And one can see, for example, that in the period between 1st of March and 21st of March, the doubling time for the reported cases was fairly constant, round about 3 days or so. And after the 21st of March, this doubling time increased, and this indicates a significant slowdown of the rate at which the reported number of cases increased. Similarly, for the reporting of the fatalities, up until the 21st of March, one could see that the doubling time was fairly constant, somewhere between 2.5 and 3 possibly. And then after the 21st of March, this doubling time also increased a little bit, though to somewhat smaller values than the values that describe the reported cases. Here currently the longest doubling times are on the order of 5 days or so. Instead of looking at the doubling times, one can also look directly at the rates and how they change with time. And the same conclusions are valid as the ones for the doubling times, of course, because the values relate to each other as their inverse quantities multiplied with some constant. The interesting observation is here that the rate of reported cases dropped from the 21st of March, starting out at about 0.23 or 23% over the course of the last 2 weeks or so, down to values well below 0.1. This is an important observation, as for the total number of active cases to go down, the rate of new cases has to drop significantly below the rate at which people get healthy again after being infected. And this rate is considered to be somewhere around 0.1 per day. Therefore, it will now become interesting in Switzerland to look not only at the number of total reported cases, but to also look at how the number of active cases reduces. The number of active cases determines the spread of the virus. When the infection rate becomes lower than the rate at which people get healthy again, then the number of active cases will be reduced, and only then the epidemic can be stopped.